Hello, so welcome back everyone to this lecture series on Julia. Today we will be looking at an interesting application. Today is a video on an advanced assignment on coding with Julia and just algebraic structures with Julia. So to start with, I want you to take a look at this YouTube lecture which is linked in our notebook. And yeah, so this lecture is an excellent introduction to quantum groups, which is what we'll be trying to, code up today. And yes, so quantum groups will be explained very well here along with, I advise you to see the whole lecture through to through. And today, along with explaining what a quantum group is, I will also show you how to code it. Okay, so just undo this here. So scrolling all the way up. Yeah. Okay, so since this is not purely an algebra course, I wanted to mention some links anyway. So this is a good lecture. This is my favorite, one of my favorite YouTubers. This is a really good in-depth lecture on what a Hopf algebra is. Then if you watch this will make a lot of sense because you'll have your Hopf algebra background. So if you want to just have something fixed, something organized, right? So today's assignment, today we will be using, I'll explain a little bit on the assignment. I'll try my best to explain what the assignment is asking. So there is an algebraic object called a quantum group. Okay, this arises in systems that try to, like whenever we try to mathematically represent a quantum system, we end up getting quantum groups in some very special cases. So what is a quantum group? And that I'll explain what a quantum group is. We'll be looking specifically at this example of a quantum group, and we will be, solving an equation called the Yang-Baxter equation. So the Yang-Baxter equation is a equation. Let me just start drawing. Yeah. Okay. So are you? Yeah. The Yang-Baxter quantum. Oh wow, that's writing terribly. Yang-Baxter quantum equation. Yeah. So this equation is a relation between a matrix called an R matrix. Oh god, no, don't zoom in. Yeah. God help me. Okay. Yang-Baxter quantum equation. Yes. So this is an equation relating the R matrix, which is, oh, why does it zoom? Can you unzoom for the love of God? Okay, so it relates the R matrix acting on, say you have three, tensor groups v1, v2, v3. Now, why am I saying tensor groups? You say you have three spaces v1, v2, v3. The Yang-Baxter equation is going to tell you how the tensor product of these vector spaces should satisfy in order to preserve braiding of any two quantum systems. Okay, so I will start at the beginning by just explaining. This is an overall high level picture of what's going on. Okay, from now I will start to explain what is going on. Okay, so the goal of the assignment is to use the quantum, this special case of a quantum group, and we're going to learn to initialize this as an object in Julia. Moreover, we will look at using this verify the Yang-Baxter equation. So let me start to explain what a quantum group is. Okay, so in physics, when suppose we have a qubit, let me draw for a second, and I would also like to draw really thick. Yeah, so yeah, suppose you have a vector 0, right? I've said vector. On this qubit you can perform certain actions. That is, either you can, increase it slightly, which we would say as the action of adding or the action of raising. Okay, secondly, you can lower it, and thirdly, you can measure your qubit. Okay, so, and this is for raising. So these are basically operators acting on your qubit over here, and depending on which operator you use, you can express any qubit, right? So if I wanted to express 0 as 1, I would just repeatedly raise it. So I would repeatedly apply E over and over again, and then I would eventually get 1. But once I reach 1, I cannot raise it any higher because there's nothing higher than, 1. Do not have, yeah. And then similarly, you can lower it using F until you reach 0. So these two operators are called ladder operations. Specifically because a ladder has a top and a bottom, so that means that there are limits to how much you can repeatedly add them. So I can repeatedly add them, and I can repeatedly lower them until I reach 0, beyond which I cannot lower any further, and I can repeatedly add them until I reach 1, and I cannot raise any higher. Okay, so, and at any given point in the middle of this process, I can measure the qubit to collapse the state. Okay, so here's some little more in-depth explanation of what's going on. This is the basic thing. So what I want you to pay attention to is that you have F and you have K that is acting on a state X. Okay, now X is a state, right? And typically in physics, we like to talk about state space. So let me just write that down, state space. Oh man, I did the drawing thing again. Yeah, there you go. Yeah. So the state space is supposed to be set of all possible values of X. So I can say it's the same as X belongs to a larger set, capital X. Okay. Now when this say, what do you say? This is now just simply a set, right? And a very sets are the foundation of math. So no matter what structure you're looking at, it's going to have some structure higher than a set. Okay, set is the most general thing. You can have a topology, a group, many things. So the magic of quantum groups arises when you say, "Ki, what if X is a group, has the structure of a group?" And so in physics, when we're studying a classical system, we have the state of the state space of all possible states. And you have an algebra of state space, so you could say of X. What is the function at play over there? So if I'm going from, let's not call it X, let's call it rest, okay? I'm going from rest to motion, okay? Very simple example. Let's reset again. I should kill the person who made the set thing, okay? Anyways, let's not say that. So, where am I now? I'm in Zoom again. See, it's going to be an irritating thing. Anyways, so from rest to motion, right? Yeah. So what is this function over here? That is acceleration, right? So acceleration now, A belongs to O of X, such that O of X is the functions between states. Okay, now let me now let me erase things a little bit to make space, because there isn't any. So okay, this part is clear, I think. Okay, and now we know what O of X and X is. So with that in mind, similarly, let's draw. Similarly, I explained like with the example of X, rest and motion, right? So similarly, where is my mouse? Yeah, there it is. Okay, so similarly, if I had the 0 get, if I add E, right, eventually I should get 1, right? So these both are individually states, and this E is going to belong to O of X. Okay, so a lot of this material, if you watch that I put on quantum groups in the link in the notebook, then it'll make a lot of sense, because a lot of it is directly from that. That guy explained it pretty well. So E belongs to, oh, I forgot to put the belongs to symbol. E belongs to O of X, okay? So the structure that O of X forms is called algebra, okay? And the generators of the algebra are these guys. Oh, a little bit too back. Can I undo that? Yeah, there we go. Yeah, the structure, the generators of your coalgebra are these guys, okay? So reminding you again, raising, lowering, and measuring, okay? So now I'm going to, yeah, okay. So let me just erase everything, exit drawing. Yeah. Okay, so I've explained what the ladder operators are, lowering operator, raising operator, yes. One more practical example of these operators is in this system over here, this physical state, where you want to, what do you say, you want to measure energy levels without solving Schrodinger's differential equation. Rather than finding the energy level by solving Schrodinger's, instead you continuously use the adding operator, the raising operator, or the lowering operator. In this case, they're not called the raising and lowering operator, they're called the creation and annihilation operator, okay? So just a change of name. Okay, see over here, raising and creation. And since they're operators are matrices. So if the operator is A, then A dagger. Oh no, let's go back. Yeah, so yeah, dagger is our creation operator. Alright, so yeah, why are they important? Because they help you solve Schrodinger constructing states, and they're also used for QFT, where you want to create and destroy particles in vacuum. This is important for things like pseudo particles. If you go small enough, things coming back out of existence. So just to model that part as noise. Yeah, anyways, so what is a quantum group? Okay, it's not a group in a traditional sense, it is only a group. You remember, our state space becomes G, so our state space X becomes a group. Okay, and the term quantum group is not really that well agreed on, because it is a fairly new topic in general. But what happens is, over here I talked about O of X, right, being a, okay, it is basically a type of opposite of an algebra. So get this, in category theory, if you have a concept like say a concept of multiplication, all right, this example makes sense. Hello, yeah. So what I was saying earlier is that suppose you have a concept in category theory such as multiplication, okay, takes two objects A, B, multiplies them into some other object, okay? Let's just call it A, B, okay. Similarly, the opposite of multiplication is called co-multiplication, okay, and this takes your object A and it gives you two objects A and B separate, okay. So this is where you say, so anything co means anything like with the suffix co, co, means that it's the opposite of that concept. So if you had co-multiplication, you have the opposite of co. If you had co-algebra, then that means it's the opposite of an normal algebra. Okay, what an Hopf algebra is over here is it's an algebra which is both, and it combines these both structures of an algebra and a co-algebra by combining the operators of multiplication and co-multiplication. Okay, now this multiplication and co-multiplication, these are, oh wait, I used the wrong thing for multiplication. Let me erase it. Mu. Alright, so these two are opposite things, okay, both of them. And when you combine these two structures together and you define the relations, then you get Hopf algebra. Now, let me erase everything. Yeah, okay, there you go. So, what a quantum group is when you take a Hopf algebra and you start to deform it. So, suppose you have a nice looking Hopf algebra, okay, over here. And you start to deform it slowly, so you get something like this. Oh no, God forbid, we're zooming again. He said zoom, please, for the love of God. Yeah. So it takes your structure over here, your nice, clean, well-defined structure, and it deforms it, okay? What it deforms it is based on a parameter called h. So if h is equal to 0, and when h is not equal to 0, okay? So depending on this value of h, you get different structures. And these collective structures are all called quantum groups. Okay, now for simplicity's sake, we can, what do you say? Okay, so one example is to take the special linear group called SL2 and to deform it. So what you get is, depending on whatever you're parameterizing, so if h is equal to I, then you have, if you have h is equal to 1, then you have u1 of SL2. Okay, so what we're gonna do today is we're gonna use the representation of 2, right? Give us something called an R matrix. And what we're gonna do is we're gonna use this R matrix to test our Yang-Baxter equation. Okay, so let me erase everything and let me start scrolling. Exit drawing. So yeah, so over here, look, our example is SL of SL2, which is a deformation of the algebra of SL2. Okay, and we have another, parameter Q. So instead of just using h and waiting for h to equal to 0, we take Q such that Q is equal to e to the power of h. And whenever h is equal to 0, e to the power of h becomes e to the power of 0. Anything to the power of 0 is 1. So q becomes 1. Okay. So instead we say as q goes to 1, our structure becomes that nice round thing that I showed you. Okay. Now we're going to take our generators, which is e, k. So I told you earlier that if you have some qubit and you continuously apply e, then you can get everything that is equal to 0, right? All the states between 0 and 1. Okay, and similarly when you just measure them, it just projects some number. So over here it'll just give you 0, over here it'll give you 1, then k will give you some number between 0 and 1. Okay, so all this to say, we need to start putting relations between how e, f and k interact with each other. That's how we will define our group structure. Okay, so yes, there's a button. Yeah. So these will be our relations. This is what we're going to focus on. What do you say? These axioms we will learn to put in Julia. Along with that, all of these are axioms that we have to put in algebra. In Julia, we will be defining what k and k is, all right, or at least we'll define the relations. And finally, we hope to find the matrix R. So to find the matrix R, we use this thing over here. You see the tensor product over here. You see our generators over here. You see our number q over there, which is given to us, remember? And we see something called a q factorial over here. So that I'll explain in a bit. See, again, q to the power of the tensor product of h across h divided by 2. So where was I? Yeah. So our main aim is the Yang-Baxter equation. These individual terms are all, oh god, again it went there. Okay, these individual terms are all matrices such that it is the action of the first tensor space okay, wait. It's the tensor product of the first space with the second space. Okay, here, that's why it's written over here, the space and the jth space ka product. Okay, now first thing is we're going to create structure of our elements, and we're going to find a way to express what our generators are. Okay, so we're probably going to use just dictionaries for a simple approach. This is going to be easy only. Then we're going to define our R matrix. We're going to have R get calculated over here. For this program, I decided to stick with just with 3 or 4 because anything higher, I wanted to keep it accessible enough so that it's the demo is there. So it's more important that we understand how to implement such a complicated algebraic structure before we start worrying about results. Okay, so if we go higher, then we'll get closer to the equality. Otherwise, it'll just be approximately the same. So we decided to leave that. Okay. Now, one definition I thought was necessary to put was, what is it? A Q number is a deformation of the number. So wait, let me show you. Okay. So during this deformation has a term, it's called quantization. Every time I click, I get worried if it's gonna zoom. Okay. Now, in this nice algebra, we have a regular ground field, which is, say, for example, just real numbers, right? 1, 2, 3, 4, and so on, right? What happens to our ground field as we call is what we call the Q numbers. Okay, now where is it? Yeah, they appear everywhere. You need to. So, and the Q number, so suppose n was 1. Okay, let's just take an example. So we define a Q number, which is the deformation of the number n under the parameter Q. Okay, this is why we use Q rather than h, because when we use h we have to include e to the power of this and all that. Huge issue. So q to the power minus n the whole divided by q minus q. For simplicity, let's say q is equal to 1, which is our classical case, right? We're going to show ki our deformation goes to our regular numbers. So if we deform it under q is equal to 1, it goes to our classical case. In our classical case, we have the regular numbers. Where is it? Yeah, 1, 2, 3. So if we put in the classical case, what we should get is that if I put in 1, I should get 1. If I put in 2, I should get 2, 3, and 3. Okay. So we're going to prove that. Okay. So let q equal to 1. Then that just means q to the power of n is 1 to the power of n minus 1 to the power of minus n. So that is the root, right? I don't have space. Yeah, there we go. It's equal to 1 minus 1 inverse. So for this, instead we use L'Hospital's rule. I suddenly feel lazy to go with it because I do want to move on instead of completing the entire proof. But if you solve this, then you should just get that your limit is evaluating to n. Okay, so instead of just having 0, 0 over here. Alright, so with that said, we know what a q number is, which is n deformed by q. We also know what, now we're going to define what an q factorial is, which is this number over here, and this is the product of similar to a factorial only, except everything is deformed by q. Okay, that's why it's mentioned over here. See. Okay, now what is left? Yes, we will be explaining what a tensor operation is. And then, yes, finally, we'll be writing our Yang-Baxter equation. Now, I mentioned something, a little thing I want to go to before we jump right in is I want to explain what the Yang-Baxter equation is. So the Yang-Baxter equation allows you to take 3 spaces, and it allows you to show that braiding of any two systems is preserved. So this is a picture of Yang-Baxter equation. It comes up in mathematical physics and it is quite an important result. So as you can see here, changing the order of our braiding by moving this middle one over here to the other side preserves the system. So by swapping 2 strands, we can swap 3 strands in 2 different ways. And the Yang-Baxter equation shows that these two are the same thing. Okay, so with that in mind, over here, see, it is given as the scattering matrix, which is the R matrix that we were talking about, our representation matrix, right? Let's close this as well. Okay, so yes, this is a simplified implementation structure. Yeah, we will be using our library linear algebra. Okay, so first structure. This is to define tensor products and stuff, makes it easy. So we define our group, an element in group, okay? So what we want for each element is the number of k generators, the number of e generators, and the number of f generators, right? So that's why the power. And we also want, yeah, this is a sparse representation, okay? So terms, dictionary, we have tuple containing 3 integers such that some of them are such that they are, what do you say, 64-bit. And a 64-bit complex number. So q is going to be that number. Okay, so any given element inside our quantum group is going to have 4 what do you say, what is that called, 4 values, right? So 3 of them are the generators, and the last one is our deformation parameter, which is q. Okay, now we're going to define each of our generators. So I said 4 values, right? 3 of them are generators, so these 3 are what we're going to focus on. Okay, so over here you can see EQ is defined as a dictionary that takes 0 and 0 to 1 0 with Q. Okay, similarly F takes that to that. All these relations are defined. Okay, now the inverse of K is also defined over here. See, you're understanding, right? Over here we took a tuple of 3 integers. So when the middle integer you remember over here, see, K and then E and then F. Okay, so over here, this will have K, this will have E, this will have F. Wait, I should probably draw it. Yeah, is it working? Yeah. So this is it visible even? It's barely visible. Let me just use the pen. And K is also over here. Okay. Now I'm going to exit drawing and I'm going to do the same thing again. Is it working? Yeah. E. Alright. The middle one. So E is the middle integer and E is defined over here. See? Lastly, you can check for F as well. F is the last one and it is over here. Okay. So what we're doing over here is we're showing that we're showing which one it goes to. Okay, and this is under our classical one where, like, Q is equal to 1. Okay, now let me exit here. Okay, so the inverse is also defined where the power is -1 instead. Okay, now base 1. Okay, we're gonna define an X belonging to an element such that we call our element now, and we have a dictionary with all our parameters as 0 and our quantization is 1. Okay, now we're overloading our operators so that we can do, we can explain multiplication, co-multiplication, stuff like that, because we're defining a new algebra, right? So we have to make sure we define all our operations. So multiplication, addition, subtraction, and assignment or equality. Okay, so over here, see, we're overloading our multiplication by calling the function such that we're calling a function, and over here there would normally be a function name, but instead we're overloading our operation, which is an asterisk. Okay, we want our asterisk to take 2 elements this time from UHSL2. So this makes sure that if you had any 2 random normal numbers, it's going to multiply the same as before. 1 into 2 is still equal to 2. But if your elements are coming from UHSL2, then only it's going to apply this version of multiplication. Okay, so only if and only if both the elements are from this data type. Now we're going to define all our terms. If x terms are equal to this and y is equal to this. Yes, so this is where we start putting our relations. Okay, so we want to show that the action is almost commutative except for this little thing over here, right? So this is how we define our multiplication between E and F. Okay, so this definition of multiplication happens if and only if what we're multiplying is F, or F and then E. Okay, return this. See, now in the default placeholder for general multiplication. So if you just have normal multiplication, then you're just gonna whatever is the product. Okay, now we're gonna define our co-product. So if we have Q, we're going to split it. So we're gonna split it into X and Q. This shows the co-product for generators. X is equal to terms, return 1 EQ represents this. Okay, see, one by one we're satisfying our relations. So let me show you. So the first relation is this tensor product addition, right? Similarly, this tensor product and this tensor product is applied alone. Okay, so yeah, 1x, this represents our identity. Okay, 1 is an identity. This is the rest of our axiom. So this is how we write, this is how we explain what we're doing. Okay, square brackets stand for tensor product. Okay, now if we wanted to apply antipode and count it, we would do the same thing. We would write our equations such that if the number of terms in X is equal to the number of E terms in Q, then we would return the relative, the respective relation. Okay, and we would define co-products like that. For demonstration, we will go with the simplified version. Okay, so we define a new function that is to find the R matrix, and we're going to the value of Q, and we're going to get the number of terms that we need. Okay, so Q is equal to that complex number that we defined way back in the beginning of our program, and our terms are now defined by this. What do you say? So defined by this, the tensor product of E and F, and our terms is our terms is equal to tensor product of E and F divided by this, right? Cool. Yeah, so in a full version we would loop to n terms calculating Q factorials. Instead, in this version we're not going to. We would need the functions to multiply these Q tensor elements and check YB. This is a very hard to compute task, so we're gonna print just that. Okay, then we're going to show that it's 0.5. We've set the value of H to half. Okay, now then we're going to show the co-product of E, and then we're going to, we're just going to print, and we're going to run our application. Alright, so thank you for listening. This was an advanced application on how to write Julia code, or how to model a quantum group. Okay, so these are all the relations. Everything that you need for understanding this, or most things that you need, will be given here. Okay, if you need a little more background in what groups are and what rings and just algebra in general is, then you can go to these set of lectures. And one thing I recommend is, if you need to find YouTube videos talking about any given topic, just click on one lecture, say from Oxford's playlist, and just let it run all day. YouTube will think you like that stuff, and soon you'll have pretty good recommendations. So thank you for watching, and I will see you in the next class.